Okay, we are in 1.4 and this is composition of functions. If you have not watched the arithmetic combination of functions video yet, then you need to watch that first. I prefer that you watch this one second. This is the back half of 1.4 and this is on combining functions in a different way. If you watched the first lecture, then that was on combining functions with arithmetic basically, right? So this is a different type of combination. This is called composition of functions. And this one is actually we take one function and sort of put it inside of the other function. So some of the notation that we use is this, it's said f composed with g. And so this little open dot means composition, not multiplication. Like if I wrote f times g, it would be with just a single dot. But when you have this little tiny open circle, then that means composition. So this first one is read f composed with g, and this one is read g composed with f. Okay, so the way that I make better sense of this in my brain is to write it, this is another way to write f composed with g. It means f, we say f of g of x. Just like if we said f of 3, this is f of g of x. Now we've had some experience with this notation before. Like when we did f of x plus h, we took the x plus h and put it in for x. This is a very similar thing. It's just we're taking a whole function, a different function named g, and putting it in for x when we deal with f. So, for instance, if I let f be x plus 1 and g be x cubed, then f composed with g, f of g of x, means another way that I could write this is f and then my new x, f of x cubed. G is x cubed, so I'm just replacing g with x cubed. And so now this notation says, everywhere I find an x here in f, I'm going to put this in for it. And so this is x cubed plus 1 is f of g of x. Order really matters when I'm composing two functions like this. So it matters which goes in first because I'll get possibly two distinct functions. There's an occasion when I get the same thing in either direction, but that's a special type of function. Okay, so I have f composed with g is x cubed plus 1. Okay, so if I do this in the opposite direction, I have g composed with f. So again, my f is x plus 1, g is x cubed. Now I have written up here, I didn't talk about it here, in this first one, f composed with g, we say that f is the outer function and g is the inner. It means I'm going to put g inside of f. And so when I come down here to g composed with f, this time g is going to be my outer function and f will be my inner function. I'm going to take f and put it inside of g. Alright, so g composed with f this time. I can rewrite this first as g composed. Instead of f of x, I'm going to take what f of x is equal to and put in x plus 1. G of x plus 1 is, I'm going to take g, which is x cubed, so this is my new x cubed. Okay? So my g composed with f is just x plus 1 quantity cubed. Now I could multiply this out 3 times and get something different, but I'm okay with just leaving it right with this for right now. Okay? We always work basically from the inside out. So g of f of 2, all right? Now, g of f of 2, actually what that means is this is g composed with f, right? I can write it like this. So g of f of 2 means that if I put g of f of 2 in here instead of x, then that means I take the 2 and plug it in for x. So that would be 2 plus 1 cubed, which is 3 cubed, which is 27. Now, if I didn't go to all the trouble, it wasn't that much trouble, I guess, but sometimes putting them together can be a little bit algebraically challenging. If I had just been asked for g of f of 2, then I work for them the inside out. So here I already had g of f of x, and I just popped in the 2. But if I didn't have that, then I want to show that we get the same thing. We work from the inside out. So the inside says f of 2. Right, so if I come back up here and I look again at f, f is x plus 1. So f of 2 would be 2 plus 1. So f of 2 would be 3. So then now I'm going to replace f of 2 with 3. And then I have g of 3. Okay? Again, g is this x cubed. So when I plug in 3, I get 3 cubed, which is 27. Right? So I get the same thing. So what I'm trying to say here is if I'm just looking to evaluate it at one point, then I can just plug them in that direction. If I'm going to look to do multiple things, maybe I want g of f of 4 and g of f of 6 and g of f of 10, then it will probably be easier for me to create this, right? Now, if I'm just asked for g of f of x, then of course I have to do this. But if I'm just looking for a value, then I can just work it in this direction. Either way will work, okay? All right, so now we found that when we were dealing with functions that were combined with arithmetic, then the domain was the overlapping. So it was the things that were common to both, unless we were dividing, and then we also had to throw out any place where the denominator was equal to 0. Now, f composed with g and g composed with f can come up with completely different domains, and it a lot of times just depends on which function is the inside function versus the outside function. So, a general rule of thumb, now the first example that we did, we had f and g, right? And neither one of these particular functions have domain restrictions on them because there's no square root, there's no division by an x. So normally, if I don't have any kind of original domain restriction, then when I combine them, I'm not going to have a domain restriction. Now this one is a little bit different because now my f is fine, right? I have f is x squared, but my g has an original domain restriction on it that says that this must be true. So x is greater than or equal to 2. Now if I was adding f and g, then f and g would have this also domain restriction on it, or subtracting it. But when I'm combining them, now I may have something completely different. Okay. So for instance, let's look at first f of g of x. Okay. So if I have f of g of x, then this means I'm going to take g and put it in for my f. So here I go with, I'm going to write it in steps here. I have f of x minus the square root of x minus 2. That's my g. So when I combine these, I'm going to get here, let me take away that. So my x is this, so I have the square root of x minus 2 quantity squared. Now, when I square this, I get x minus 2. So this is f composed with g. Now, upon looking at this, I think, oh, wait, there's no domain restriction here. But if I tried to do, for instance, f of g of, let's say, 0, okay, and I try to do it without making the combination, then when I go to plug in, like my last example, the g of 0 means I plug in 0 here. And I'm immediately going to get, if I try to do g of 0, I get the square root of negative 2, okay? So this is a problem because the square root of x minus 2 is my inner function. So that's where my value of x goes first. So because of that, this also has to have the domain restriction on it that x has to be greater than or equal to 2. Because the first thing that happens is a number gets plugged into the square root. Okay? So this is a little bit tricky, so you need to make sure that you're looking at what is going, where's my x going first? Excuse me. Okay, so if I do it in the opposite direction, I look at g composed with f. This time I'm going to have f going into g. So that means I'm going to have g of, let me write x squared here, right? Because that's now my f. So I have g of x squared. So I take my g, which is the square root of x minus 2, and instead of x, I'm going to have x squared minus 2. Okay. Now this one is a little bit different because now I have a new function again. So my inner function is not an issue, right? If I just look at the x squared minus 2, I can plug in whatever I want out of that. But this now has a new g composed with f has a domain restriction because I know that x squared minus 2 has to be greater than or equal to 0. So that means that x squared minus 2, I'm going to look for my 0 first. So x squared equals 2, and I get x equals plus and minus radical 2. So again, if you need a refresher on quadratic inequalities, go back and rewatch that lecture. This gives me negative radical 2 here and positive radical 2 here. And when I check out values here, I should get, let's see, if I plug in, for instance, 5 back here, right, because this is like 1.41. If I plug in x as 5, then I'm going to get a positive number. Or negative 5, I'm sorry. And if I plug in 5, I get the same thing, because when I square it, I'm always going to get 25, whether I put in negative 5 or 5. If I plug in 0 here in the middle, I get negative. So my domain is in the two pieces here, which I can write as an inequality as x is less than or equal to negative square root of 2, or x is greater than or equal to the square root of 2. So the general rule of thumb is that if one of my functions has a domain restriction, then more than likely my composition also has a domain restriction, but not always, okay? And it can be completely different than the one before. All right, so that is composition of functions.